Hi, this is Parag Keshav of CSC Data Science. Today our topic was communication deadlocks. What is deadlock? A deadlock happens in the operating system when two or more processes need to some resource to complete the execution that is held by the other process. A deadlock occurs if four Kaufman conditions hold true, but these conditions are not mutually exclusive. They are given as follows. A set of processes is a deadlock if each process in set is waiting for the event that only other process can cause. And here is a small example of the deadlock. Keyword error or no keyword present. Press F1 to continue. Delete to enter setup. Detection of the deadlock. Is the system deadlocked or and if so, which process are involved? The ostrich algorithm. Hope one of the processes time out and lets other to continue. This is the algorithm which one of the deadlocks. Deadlock detection with a single resource type. Construct a resource graph looking for the cycle. DUCT. Deadlock detection with the unique resources. Existing resource vector, available resource vector, current allocation matrix and request matrix. Recovery. Rollback and terminating processes. And how to avoid the deadlock, and here we are going to discuss about it. First, Mangus algorithm. Scheduling algorithm using process max allocated and available resources to avoid unsafe memory states, not practical. Banker's algorithm created by Dijkstra, our favorite. Essentially, the Banker's algorithm is about making sure a system does not run out of resources. It analyzes the resource safety of process based on three main factors: the process maximum required resources, its allocated resources, and total amount of available resources in the system. The entire goal is to keep all processes in a safe state, allowing every process to exit successfully even if they allocate the maximum number of resources. The unsafe state is when there isn't any way for the process to allocate enough resources to finish, and thus the banker's algorithm tries to avoid it. The limitation of the bankers is that is necessary process information like the total maximum number of resources the process might ever need is often unavailable. And here is a Trevor on the subject of prevention. Safe state. A scheduling order allows every process to run till exit while requesting max resources. Unsafe state. No ordering allows each process all necessary resources, not a deadlock state. How to prevent the deadlock? Now we are going to discuss about it. Mutual exclusion condition. Avoid assigning a resource and limit claiming processes. Hold and wait condition. Program a specialized resources needed by a job. Requested temporarily releases held resources. No preemption condition. Virtualize resource to follow forceful removal. Spool printer output to disk and only printed daemon printer access. Circular wait condition. Limit process to ensure one to one resource at the global number for the each resource. If we were go back to the four conditions stated by the Kaufman and the others that are required for a deadlock to occur, if we can eliminate one of them, couldn't this prevent deadlocks? If not, weakening them in a way will lower the chance of the deadlock. This is when a resource is only available to the one process. Avoid assigning a resource unless it is absolutely necessary, and try to limit the number of processes that can claim the resource. This method helps but does not completely prevent deadlocks. It reminds me of limiting a user input to prevent the unnecessary problems. This is a process allowed to request more resources when already holding one or more programmer specifies which resources are needed by a job. Then the resources are reserved until that job finishes using them. This is an extra burden for the programmer and wastes resources. But it does eliminate deadlocks. The program requesting resources temporarily releases all of its held resources, then requests all the resources it needs. This is when a resource cannot be forcibly removed from the process without the process itself initiating it. Some of the resources can be virtualized to allow forcible spooling printer output to the disk and allowing a only printer daemon access to the real printer. Eliminates deadlocks involving the printer, though it does create potential for the deadlock over disk space. Through a large disk space would make it unlikely. However, this does not work for all resources. For example, records in the databases or tables inside the operating system must be locked to use. This is the actual chain where this slice a cycle which two processes are wanting resources held by other. Why not simply limit the process to held by only one resource at a time? Well, this would sometimes break the deadlock, but will not work for the large process. The global number of each resource and they can request the resource it needs since one resource is always higher up on the ordered list. Therefore, the process holding the highest resource will either finish or use another higher ordered resource. Bug fix is that the process holding the highest ordered resource will not be requesting anything below it. The possibility of the deadlock can only the problem with this method is finding another satisfies everyone. And next is scheme with the other types of deadlocks. What is a communication deadlock? And now we are going to involve in our main topic. A process in this deadlock wait to communicate with the other process in a group of the processes. A waiting process can unblock on receiving communication from any of these processes if each process in the set to waiting to communicate with the other process in the set and no process in the set ever begins an additional communication until it receives the communication for which it is waiting. The set communication is deadlocked. A communication deadlock occurs when the process A is trying to send a message to the process B, which is trying to send one to the process C, which is trying to send one to the process A. There are various scenarios in which the situation leads to a deadlock, such as no buffers being available. Communication deadlock occurs on networks. Triggers when set the process try to communicate with other process. As I said now, no process starts any further communication until it receives the communication it is waiting for. These deadlocks cannot be prevented by ordering the resources or avoided by careful scheduling. Timeouts can be used to break the communication deadlocks. For example, suppose a process A waits to get the message from process B. Process B waits to get a message from process C, and the process C waits to get a message from the process A. Hence, a deadlock. The TFW diagram is shown below. Users in a distributed DDBS access the database data objects by the executing transactions. A transaction can be thought of a series of reads and writes performed on the data objects. A database's data objects can be considered resources that are required through looking and released by transactions. In DDBS, wait for the graph is referred to as the transaction wait for graph, TWF graph. For example, it takes money to make money. You can't get a job without experience. You can't get experience without job. A communication deadlock is a type of distributed deadlock. It occurs for a deadlock to occur, four conditions must hold: mutual exclusion, non-preemptive mode, hold and wait, cyclic wait. To prevent deadlock, one of the most assured, these conditions cannot be held. Preventing deadlock, avoiding deadlock, and these we have discussed below. Thank you.